Okay, so there was a request for the infection problem. So let's say that in a given sample we have 10 infections.
Whoa, no.
So 10 people are infected. And it's going to, let's say, based on those 10 people, each person infects 3 people per week. Okay. So that means every week there are 3 more infections. So now the question is, after a year, how many infections do we have? Now we should be able to model this and then solve it by substituting it. We could also, using what we know about solving exponential equations, go another step and actually say how long until. And but let's get this first one, and then we'll do a how long until kind of problem. So the model, f of x is going to equal, now we have our principal amount that we start with, that's 10 people, times the infection rate. So in this case, it's 3 people per week. So that's an infection rate of 300%. So when we look at our basic equation, it was f of t equals the principal amount plus 1 plus rate to the t power. So in here we're going to put the number 4. Now remember, that's because as we infect more people, we have our initial person and 3 more infections for a total of 4 times as many people at each iteration. If you're not sure on that, think of it this way. We started off with 10 people infected. Then after the first week was over, we had acquired 3 infections per infected person plus the original 10 people. That puts us at 40. Now, each of them infects somebody over the next week. So that's 3 infections per 40 people for 120, plus the initial 40. Puts us at 160. And now we can see that we're increasing by a rate of 4 with each iteration. Then we can go ahead and say that's to the t power. Now, given that equation, it's just a matter of sub and solve. After a year, which is 52 weeks...
Daddy, when you put together his club, that makes it a gong.
We're solving that equation. 10 times 4 to the 52nd power. Now, the downside to that is that's a huge number. So we're going to have to go find a calculator that will let us come up with that. So let's see, online. I don't have a calculator here.
Yeah.
Online calculator. And let's see here. That doesn't do exponents. Let's see what this does. That doesn't do exponents. And
For me.
that's a download. This is proving to take me longer than I thought it would. That's a basic calculator. Please be a working calculator I can use. Aha! Alright. There we go. So, now let's type that in. We said we were looking at 10 times 4 to the 52nd power. So, we do 10 times 4 raised to the 52nd power. Calculate. Wow. Well, I don't know about you, but I'm looking at that number, and I'm thinking we just infected the entire world a few times over. Like, frightfully so. Okay. Let's see. So back to this, we have a follow-up question. Now, basically, what this translates to is huge number. So after a year at this infection rate, it's disgusting. There's not a lot of point in having that conversation. Let's... Xander, remember Daddy's teaching. He's kind of having some fun. Now the question is, what if the rate were 3 people per week? Or 3 people per day? How that would change? Let me double check the question before I go any further.
Per
What if the rate was 3 people per day? Okay. Then what would change in the problem? So if I said, let me put a line in here, and I talked about 3 people per day. So 3 people per day. Now what that changes with this is actually not a lot, because what we're going to have is we're going to have that same rate. So the formula will look the same, 10 times 4 to the t, because it's still the initial infection plus the rate of 300%. Now, as a result, the difference now is t is no longer in terms of weeks, it's in terms of days. So when I were to set my equation up to try to figure out what my infection numbers looked like after a year, I would be working with 10 times 4 to the 364th power instead of 10 times 4 to the 52nd power. That's the only real appreciable change I would see there. Let me push this one into the